So this is the last topic lecture of the class. I didn't have a consensus on exactly which topic, but I thought that sample selection and external validity is a fairly useful one. There are concrete estimators here that you can actually go and apply to data, and you will get some use out of them. So that's the plan for today. Next class is going to be discussions, essentially. So you all are working on various sorts of projects, and we're going to take that day to let you hear about them and let you tell the class. So I'll be around after class today and at office hours tomorrow if you want to discuss anything in particular about those projects. Okay, today, sample selection and external validity. So the problem that we're trying to deal with here is that the previous causal inference methods we've talked about so far are basically about learning features of a model from data. So given some model and some data source, you want to identify and estimate a causal effect, and various assumptions on the model and the data that you have will get that for you, if you're fortunate. And that's useful. We've come up with identification formulas, estimators. Usually the point of performing some kind of statistical inference, performing some kind of causal inference, is to learn something that's applicable beyond the setting at hand. You want to, even if you're not necessarily going to be applying a policy, maybe you just want to learn something general about a particular topic. That general thing ought to be applicable to, or may be applicable to new people, new places, new times, new contexts. And trying to figure out what the relationship between the one study you did and what the kinds of things you can say based on that study or studies about these new places, new contexts, and so on is basically the class of issues that we're going to study today. And there's basically, I'm going to talk about several approaches to something that looks like a single problem. So this is something that happens all the time, and we'd like to understand why and what to do about it. So we use our favorite causal inference method to calculate some sort of effect or some sort of optimal policy. And we say, we showed identification, we showed that we're genuinely getting something that might tell us the effect of interest. We showed good properties for the estimator. And then we want to go and say, okay, what happens if you do this in another population, in another context, in another study? And we get some results. We feel like our first study was a pretty good one, and we get some results, and it turns out they're not the same. So even if we're doing just a pure prediction problem, if we're doing a decision problem, if we're trying to learn some causal effect, we got what we thought was a good estimate, and then we tried it one more time, and it stopped working. So you ran a behavioral experiment in a lab, you found a strong result, And then another lab ran, as far as they can tell, the same experiment, and they found nothing. This is the norm. You test a program in a randomized controlled trial in one province, and you get good results. You found out that this policy genuinely helps kids read or whatever it is you're doing. And so the other provinces say, that sounds great, let's do it. The federal government gets involved and says, great, let's make this a national program. And they implement it. And the thing that worked really well, according to your well-designed study in Kerala, ends up doing really poorly in Bihar, and nobody participates, and nobody likes it, and everybody's saying you wasted the government's time and money. Finance, you found a pricing factor. It generates substantial excess returns in all your back tests. You have some sort of strong theory behind it, something going on with risk or institutions or whatever it is that finance people like nowadays. And you start a hedge fund, you trade on it, and immediately for the next 20 years, your amazing back-tested trading strategy substantially underperforms chimp throwing darts. Could name some academics, could name some hedge funds that have found themselves in this situation. So what went wrong? And the answer is that it's probably not just one thing. Probably there were several things that changed. And so our goal today is basically to figure out at least some of the kinds of things that can change and describe what we can do about them. So issue one, what seems like the ideal case from the point of statistical theory, your new setting, identical in distribution. The new data comes from the same model, the same distribution as the old one. So there's nothing systematic going on. Your probability model is correctly specified. We're in that lovely, lovely world of the theoretical statisticians where that happens. But you didn't have a probability distribution, you had an estimate. And it turns out that the properties of an estimate and the properties of a distribution are not necessarily the same. So this is the problem of generalization. And so this is something that's extremely well studied, extremely fundamental to statistics, and yet I would argue is in many ways underappreciated by practitioners who often don't like to think of sort of maybe these more fundamental, more boring things, that uncertainty is a part of what happens when we conduct studies, but it should always be kept in mind. An estimate is not the population. And it can differ in substantial ways. Case two, new setting, new distribution. There's some attributes that you can describe that do not reflect the properties of the distribution in which you came up with your estimate, that are, genuinely, there's a different causal model in at least some ways. So this is the problem of external validity, or more generally of transportation of causal effects. And so the setting that we're going to have to deal with here is where we're dealing not just with one causal model, but with multiple causal models reflecting the different settings. And there's lots of sorts of explanations for why there might be genuinely different effects in different contexts. So the people to whom the policy is applied, the all sorts of their attributes, the program itself that you're applying, all of these may be different in some way. And then finally, this is a little bit of a related but slightly distinct case, which is that the populations that you're dealing with are the same in the sense of they're coming from the same distribution, but the data you got was not representative of that distribution in some way. So there are systematic differences in the observed sampling distribution that you use to construct your estimates, and the distribution induced by the causal model in terms of what's going on in the population. And so this is the problem of sample selection. And there are various ways that that can occur. All three of these are probably going on at once, along with other problems that I didn't think to mention when you're facing a problem like this. But I'll try and describe them one by one and describe some strategies that people have proposed to mitigate some of these issues. So generalization, this is classic statistics. We want to go from a single study to a new observation from sample to population. So because the population, we can think about it as what is the population, but just the collection of all possible new samples. That's equivalent to say that we're going from the sample to population to say we're going from sample to new samples. At least in terms of the distributional properties of those new samples. So we described a procedure or a perspective that's fairly nice, that's in which these generalization ideas have been well studied, in which we can measure the performance of an estimator or a policy in terms of a distribution, and that's statistical decision theory. We could consider other types of decision theory as well. But in the setting, we'll measure the performance by some kind of measure of risk. This is the expectation under the true model, p theta, whatever that is, of some measure of the loss. That's a measure of the realized quality of our policy, where this expectation is with respect to the unknown distribution of samples from the population. So we apply the same estimator policy to new data point. And we want to know how it performs on average. Taking the average of a function will allow us to account for risk and all these other things. So that's potentially a useful thing that we might want. It's a criterion, or at least it's a collection of criteria indexed by theta. And we can't simply optimize this criterion because it is a collection. And more practically, we just don't know the distribution. We'd like this to hold for arbitrary distributions, and so we'd like so in practice, what we do is we approximate it by an approximation that we hope will hold for arbitrary distributions. And if we're taking a sampling perspective, an approximation that does that is the empirical risk. Just we replace the expectation with an average with respect to a sample, and so we'll call that our hat of our estimator or policy. And here we're using the same samples to evaluate as we use to construct x hat by whatever procedure that we came up with. Machine learning algorithm, rolling dice, taking drugs, whatever it is. We came up with a policy or an estimate. We evaluated its performance. So most of the methods that are used to try and get good performance are ones that explicitly take into account this performance measure that we have. So empirical risk minimization basically works by taking this measure of the risk and minimizing the error in sample. But the problem is that, so minimizing this approximate error. And the problem is that if we minimize this approximate error, we in general are not necessarily, well, so there's some difference in our approximation, that's understandable. But if we're using the procedure, if we're using this criterion to determine our estimator, then the performance of our estimate is going to be not, we should think, the performance measured by the single criterion, but the performance of the whole procedure that takes into account the fact that you looked at this criterion for all possible values and chose the best one. So it's necessarily the best one in your sample, regardless of the approximation error. So you may not always be using an empirical risk minimizer per se, but often you're minimizing something that's a good proxy for this. So if you're using some likelihood, you have the log likelihood function here. If there's some continuity with respect to the risk with respect to the likelihood distribution, you're going to get something similar. Likewise, GMM and all the other sort of optimization-based estimators. And so in general, there's going to be a difference between R hat and R theta. It's called the generalization gap. And this is well studied. This is, you go across the street to take any class in machine learning, most introductory classes in machine learning. I like this. I think this Hard and Rect textbook is whatever, the Berkeley Intro Machine Learning textbook. It's online, it's free, it's easily available, and importantly, it's up to date. So they have a bunch of, the best, maybe not the best possible, but roughly speaking, about as much as is known about how you can control this. So quantitative bounds on generalization error. The basic ones that you learn in an intro machine learning class handle this by, well, so this is evaluated at something's hat. You can upper bound it by the supremum of the absolute value, over some class of methods f containing x. It's clearly a valid upper bound. And then what they do is they bound either the expectation or the probability of deviation with respect to the sampling distribution of this distance. And so for these expectation-based bounds, you get something like the probability that r hat minus r maximized over f is less than epsilon is greater than 1 minus delta. And so this is saying most of the time you're close uniformly over the class. And then a lot of these bounds are distribution free, so also uniformly over the possible distributions that you can face. And so if epsilon and delta are small, this is a pretty good thing to have. Likewise, so if you do the expectation of this, if this is expectation is small, so this is not negative, small expectation is also desirable. And so there's a bunch of theorems that give quantitative upper bounds on this, tell you exactly how big epsilon is for a given delta, and they depend basically, they're decreasing in n. More data gives you better estimates. Shouldn't be all that surprising. We know for a single x, we can do something like the log large numbers that says this. Larger n, this is getting close. These are just sort of saying that, yes, you know, not just asymptotically, but for any n, we can tell you how close that is. The other thing that they depend on is a measure of complexity of the class F. So these various measures that I talked about in a previous class, so things like Rademacher complexity, entropy integrals, Chervenenko's dimension, and so on. So those are ugly, but you can look them up in a book. The implication of this is that searching over a large space of models, especially in small samples, is exactly the kind of thing that breaks these guarantees. So if the class F is big, in some sense, then, you know, our best Berkeley theorists, CMU theorists, they have the same bounds in the Mori, Rostamizadeh, and Talwalkar book is CMU folks. So if you have some hometown pride, maybe read that one. It's the same, basically the same theorems in it. The best they can do on that epsilon is not very good. And so that tells you you should be worried. How do you get it small? Well, you work with small parametric models. Linear regression, logistic regression. More modern generalization inequalities. So the supremum is clearly conservative. The supremum is clearly conservative. You could maybe hope to do better by not taking those suprema. Then you have to think. So in some sense, the supremum is a little bit of a fiction. You say, I'm dealing with all of these f's, but really you're not dealing with all of these f's. You have some procedure for choosing one. You will, you know, that procedure might somehow touch all of them by, say, minimizing over the class of f. But in some sense, you don't really care about all of them. You care about just a subset that you're going to get. And so there are bounds that may not be uniform in this sense, but can cover the procedures that people actually use. It turns out that there's been, in the past, I want to say 4 years, a bunch of recent work on this that people actually went and figured out, calculated these epsilons and deltas for things that people use that work fine in practice. And they found that, you know, the epsilons were and deltas were basically trivial. So this is like, you know, probability greater than or equal to 0 of being less than whatever the upper bound of the data is, something like that, are the things that people found. And so people came up with better bounds that work for neural networks. That's a fun story. That doesn't actually, it's worthwhile. It's a reason why you should maybe still use these neural networks, even though they have too many parameters in some sense. But we are already using small models in general in economics. Neural networks are for fancy people, mostly. And we're already using small models, and sometimes this generalization is still bad. So we'd like to improve generalization in some way. A point of these generalization error bounds is that it's not always a good idea to try to get the best performance in sample in the data. So something that, according to particular measures, so your mean squared error, what have you, is not necessarily going to be the best in terms of the new sample. And so we'd like to potentially actually get at the performance in the new data, even at the cost of in-sample performance, and that is what is known as regularization. And so there's a lot of procedures that get called regularization. Basically, anything that trades off in-sample for out-of-sample performance is called a regularizer. People joke that if there's a bug in your code, it may very well serve as regularization. It'll probably reduce your performance in some sense, but it in general won't be correlated with the generalization error. And so there are a lot of ways to do this. Classic ones restrict the complexity of the class that you're working with by constraining your model choice to a smaller set, so making sure that everything's bounded, or equivalently, economists learn the Karish-Kuhn-Tucker theorem and are forced to use it all the time in math camp. We know what a Lagrange multiplier is, so you minimize a Lagrangian with some sort of Lagrange multiplier times a function of the constraint. If we're going to be optimizing over a smaller set, constrained to a smaller set, that's equivalent to minimizing a Lagrangian with respect to the constraint with a particular constraint. And so this is is referred to as penalization in the machine learning literature. And that's another common regularization technique that gives you the lasso, ridge regression, these sorts of things. Other things that serve as regularization may be more related to the algorithm. So you don't have to necessarily return an exact global optimum. You can have an algorithm that, a classic regularization method is what's known as early stopping, which is that some of these optimization algorithms are iterative. You run them a bunch of steps, and they take a long time, days or weeks to get to the bottom. And a common thing that you can do is just say, I'm going to shut that off after 2 or 3 days. And it turns out that this makes it work better a lot of the time. So there's various sorts of theory about this. You can read about it and so work on generalization. But there's a lot of sort of things that look like hacky shortcuts that actually people find some principles behind them. So the other thing to do is you can measure the degree of overfitting to some extent. So overfitting here is another term for, so in particular, this generalization gap has a sign in general. The performance in sample is going to be worse than the performance out of sample precisely because we're minimizing the loss in sample. And so in general, the bias in our measures of performance will be towards better performance. So what we can do is try and use measures that aren't just based on the sample that we have, just using the holdout set, just taking some data. To the extent that big data is not just a cliche, one of the things that it means is that you probably have enough data in many applications that, the law of large numbers is fine even if you only use 3/4 of your data. You'll still get a pretty good estimate. And the thing you can do with that extra quarter of your data is lock it up and never touch it until your paper gets published. And then you take that extra quarter of your data and whatever you did, you then run your procedure again in that and you measure the performance there. Cross-validation does something pretty similar, except you don't lock it away entirely. That makes the analysis a little harder, but the performance sometimes a little better. If you're using one of these methods to choose among procedures, so some tuning parameter of a procedure, then things get a little more complicated because it's no longer not being touched. You're touching it at some point, and I mean, that's part of the point, but you have to take that into account in terms of analyzing the procedure jointly. But in general, you're often fitting, a small number of regularization parameters to do. So how big of a deal should this regularization be? So I'm talking about it, and machine learning people pay a lot of attention to it. The theory for machine learning, if applied to the kinds of things that people doing applied causal inference for social science actually do, suggests that we probably don't need a lot of regularization. So the ATE is a scalar parameter. Maybe we want more than a scalar, but we usually don't want much more than a scalar. The target parameter of interest in causal models is rarely all that complex. And what that often means is that uniform bounds, which hold based on a supremum over some model class, can be searching over a fairly small model class in a way which says that even without regularization, you're simple enough that you really shouldn't be worrying all that much about this. There's going to be some epsilon there, but it's going to be small. Nuisance parameters are another story. That's what double machine learning, semi-parametric methods are all about. There may be high-dimensional things, performance on those, good, bad, whatever, but it's not actually the target. And we use methods that sort of make sure that their influence is not too big. So formally, in terms of these complexity measures, so if you just have if your target is just a functional that's described by just taking a formula, an explicit formula, and plugging in the nuisance parameters, then that's just a sample average. In some cases, you do have to go through some optimization just to solve a simple system of equations to find this moment or whatever. So there's a paper on double ML for a logistic regression prediction or something. So you have a small number of coefficients to estimate there. All of this basically, so the theory for the double ML paper, if you understand what you're looking at, it says you're dealing with teeny tiny models where regularization bounds are minimal. So condition 3.3 in that paper says something about the metric entropy of your target parameter class that you're optimizing over is logarithmic. That's a really overly fancy way designed to make sure that practitioners have no clue what it means to say that you're dealing with a low-dimensional parametric model. It's like linear regression with 5 parameters. That's fine. That's what they're actually saying. Now, in principle, you could have a target parameter that's not like that. You could have a target parameter that's like the optimal policy, which is not, the optimal, 3-parameter policy, like a 2x2 tree or whatever. That's 4 parameters. But it's, over some complicated class where you actually do have to worry about this. There's a nice econometrica that just came out, which suggests that you probably should be regularizing the policy optimization problem that we talked about in the previous class about optimal policy if you want to have a reasonably complex policy. Foster and Serkanis have a sort of very general paper about, so in one of these settings where you have Niemann orthogonal moments to get rid of nuisance parameters, but you're still interested in estimating something that's maybe not so simple as a scalar, that, yeah, you can handle that, and you probably should be regularizing that. So you're getting into serious optimal policy and considering the sort of trade-offs of how simple these things are. Regularization is maybe important. For the things that people actually do in practice, you know, the theory says that probably they're going to be fine without doing much of that. And so the question is, we have a bunch of theory that says our generalization gap should be tiny. Not the kind of thing that I should be lecturing on, you know, except as a matter of curiosity. But in fact, we have holdout samples. We don't call it that. We have what are known as replication experiments. We try and do a draw from exactly the same distribution. Y given do x. That should be an unbiased holdout sample. You can estimate the performance. We estimate the generalization performance. And it's bad. Substantial difference from the estimated effects. Presumably, not all the people running replication experiments are incompetent. They've tried really hard to minimize differences between the original setup and their sampling. Did they always succeed? Maybe, maybe not. That's something we'll talk about next. Maybe so. Maybe it's just as likely the original experimenters were incompetent and they weren't controlling things. But you know, so either way, those are sort of things that you'd have to worry about. But arguably, probably this actually is a measure of generalization error. So where's the gap? What is, you know, fancy Berkeley and Carnegie Mellon machine learning researchers told me that this shouldn't happen. Well, the reason for that is that the actual procedure that we use to produce an estimate is not run GMM once, run MLE once, run a single regression. And so the model class used may not be a good measure of the generalization performance. So all of these error guarantees basically assume that you choose a procedure, then the data is gathered, so that's where the randomness is coming from, the distribution over the data, not the other way around. And so in practice, sometimes that's what happens. So in machine learning, that genuinely does happen a lot because it's something where you set up the code for your website, you let it run for a while, and then you're getting more data, and then the procedure comes up with the estimate. That's not really how most economic research works. You are sequentially updating your queries in response to the data. You look at a scatter plot. You run a regression, then you run another regression, then you run another regression. And so when you're updating your analyses adaptively, the sequential updates, we can think about what the effective size of the model space, if you're looking at the data each time, should not be thought of as the size of the model space in any one of these particular regressions, which is generally going to be something small. Take a union bound over, you know, let's say you have 5 different steps in your data analysis, you take a union bound over those 5 different steps. So that's the maximum number of things that you've sort of considered in one of your procedures. That's going to be 5 times small, which is small. If you have, you know, moderate sized data. That shouldn't be bad. The problem is that the union bound is not how you control things when you're dealing with adaptive data analysis, because had the first regression produced different results, or had looking at the scatter plot produced different results, you would have run a different regression. And so, in some sense, there's an exponentially growing space based on the results of each previous path. So this is modeled actually quite formally as a tree. We can think about it as, so they use the metaphor of the garden of forking paths from a nice short story by Borges, which is not really at all about this topic. But it is sort of described by this exponential growth. And so in general, those error bounds are bad. Exactly how bad those error bounds are is an area of fun and interesting research. There's a lot of papers coming out on tree geometry that I can point you to if you want to find the calculations. But the answer is basically you shouldn't expect the results to be good unless you're doing something which prevents this exponential growth. Holdout set, not the fanciest method that's been discovered in the machine learning literature. It's a lot simpler than all the ones that I would otherwise be talking to you about. You know, you lose maybe a constant factor of your data. You cut out a fifth of your data. You store it. You don't touch it. You tell your co-authors not to touch it. You yell at them. Something we should be doing more. Okay, so that's fine. That's like actually like the big source of most of what's going on. But now I have to come up with what are the excuses? So people have a professional incentive to justify the validity of their own findings, and they have a tendency to see patterns in noise. You look at a cloud and you see an animal. You look at a data set and you see a significant finding. So probably what we're mostly doing is misattributing generalization failures to systematic scientific differences that we can get a new paper out of and continue publishing and not have to say that that paper that your friend published was probably nonsense. And all those papers that all your friends published are probably nonsense, even if you're a macroeconomist and, well, statistically, probably all your friends are publishing nonsense and you are too. But people say that that's not the only possible explanation. Maybe just the person running the replication didn't have the skill to run the protocol precisely. I heard, I'm not going to name names, they're talking about some behavioral bias which was found. There are some papers that said, this is a general feature of human cognition. Humans behave this way. And then the replication studies came in. And so the original paper was from an author in one city. The replication study was from, I think, a university 5 miles away. And what I heard was, oh, of course, because the undergrads at institution A in Raleigh and the undergrads at institution B are so different from each other, they have such different attitudes, that of course this bias would show up in Raleigh but not in Durham, or Durham but not in Raleigh. Maybe. Finance people, my factor really did generate alpha. Between 1999 and 2014, and then people found out about it and they traded on it, and now of course you can't generate alpha that way. So my study was fine, but we shouldn't we shouldn't rely on it in the future. Maybe that's true. I mean, I think that's probably a thing that happens. You would see the same thing if you didn't find a factor that had temporary alpha, and instead you found some random numbers. So how do we distinguish? There are measurable differences across settings. And if we want to take these claims at least somewhat seriously, we should figure out how to measure how those measurable differences have effects on the things that we see. And so this is sometimes referred to as distribution shift. This is a phrase that machine learning people use. That's a very general phrase that just means there's a different distribution in the place where we're evaluating it and the case where we fit the data. For a causal effect, we're actually interested in more than just a different distribution. We might be interested in a different causal model. Data is described by causal model M. New data is caused by model M star. A causal model induces a distribution of observed outcomes. It also induces a distribution of counterfactual outcomes. And so these are the things that both might be subject to distribution shift. Usually we're estimating some sort of functional of this causal model. If it takes the same value in both distributions, then we say that our estimate is externally valid. And so this is a weaker condition than saying that the distributions are the same. It's saying that whatever distributional differences there are not ones that affect the functional of interest. And so the question should be, when can we get results that are externally valid? So for example, maybe our parameter is the average potential outcome, expectation y given do x equals x, theta, and theta star is the average potential outcome in M star as opposed to M. Theta, we've done the hard work. It's identified in M. Maybe we ran an experiment. Maybe we found an interesting instrument. Maybe we found the setting where parallel trends actually works and we identified it. And theta equals theta star. This can hold even when M does not equal M star. And so this is sort of what we're going to try and find. What differences in M can lead theta to equal theta star. Note that in the setting, so generalization error doesn't disappear as a source of differences, but the difference in the estimate from one population, the outcome in another, is equal to just the generalization error in the former, because the population value is the same in either. And so there's no additional concern about generalization error. It's the same as it would be if we were working with the same population. Examples of this: suppose we run an experiment on a bunch of freshmen taking Psych 101 at some US university. We measure an average treatment effect. We take a difference in means. Good estimator. And then we care about, we design some stimulus that's supposed to tell us something about economic behavior. So really, what we care about is the behavior of business professionals and their work environment when they're exposed to that stimulus. Our study has external validity, for example, if the response that these US undergrads take, responding to the stimulus for extra credit for their Psych 101 class is the same as the response of these professionals. And that might be the case if this is, some universal feature of human behavior where it doesn't matter who's doing it, it's just it's just something that is broadly descriptive. A drug tested on medical volunteers, screened for health status, known biologically relevant indicators. You go through a big screening process, you have them sign a bunch of forms, you run an experiment on them, you give some of them a pill, you give some of them not. You go through the process, you give that drug to new patients who have the same indicators that you use to screen, and you say that maybe the effects of this drug will be the same because we know that there is some sort of whatever protein, genetic, something pathway that really shouldn't differ across our convenience, our sample of whoever volunteered, and people that we're dealing with. So these are stories that may or may not be plausible. If you have the kinds of prejudices that I do, maybe the second might be more plausible than the first. No offense to people who may have other prejudices. But they both depend on structural causal knowledge of the relevant populations, and we'd like to be able to evaluate that formally and see what models can say about that. So in order to do that, we'll talk about the framework of transportability, which goes beyond external validity. It's a sufficient condition for not having to worry about systematic differences between our estimates and our applications, but it's also a very limited special case. So it's only slightly less stringent than independent sampling. It says the thetas are the same as opposed to the m's. Maybe somewhat less. So maybe in some applications substantially less stringent, but in general, it's pretty strong. And so what we'd like to do instead is, well, if we know what the two causal models are, or at least enough features of them that we can say something interesting, we might use that knowledge to say, okay, maybe it doesn't have to be the same. Really what we want is to identify the causal effect in model M star, given the knowledge that we have of model M and the observations for model M, and potentially some information from M star. So our goal formally is to come up with a formula which expresses theta star in terms of quantities we know or can estimate from both populations. This is about combining data rather than taking one set of data and using it in another place. So this idea is called transportation of causal effect estimates, and effects identifiable from the pair of causal models and set of observables we have are called transportable. And so external validity is a special case of this. You might see this referred to as effects that are directly transportable, so without changing the estimate. Judea and Elias have a bunch of papers on this. I say 2014, but probably read the survey paper that's highlighted in the syllabus rather than I'm going to list like a whole bunch of papers which were the original papers. Probably not even the original papers, they sort of spread everything out. But anyway, read the survey paper because it's all sort of spread out over a bunch of different papers. But they formalized this, so they had this structural causal model set up, represented by these systems of equations with error terms, and so you have a pair M and M star of structural causal models representing what we refer to as the source and target population. Source is maybe where we have some data. Target is where we want to estimate an effect. The source has structural functions F1 through Fp, error terms U1 through Up with some distributions. The target equivalent F1 star through Fp star, distributions F1 star through Fp star of errors. We'll assume for simplicity they do that the structure is the same in terms of which F's exist. You could sort of, go further than that and say that there are potentially different F's across them, not just in terms of the actual functional forms, but potentially the causal structure. But for now, we'll just say it's the forms that are different. So the causal effects might not be the same, or the distributions of the errors might not be the same. So you have observational data, experimental data from the source distribution, and maybe some possibly incomplete data from the target distribution. So maybe we have observational studies. We see Yj through P. We can observe the joint distribution there. Maybe we have a couple of experiments in the source model. So we have some set of variables K, some subset for which we observe experimental data. And we have some subset, at least, of observables in the target population. Maybe not all of them. Maybe we have, the covariates, but not the outcomes is a common setting. We have this. And so our goal is to estimate causal functional theta star, or theta, in the target distribution P star. Something like P star y given do x. Conditional observed C. If it can be expressed uniquely in terms of observed components of the source and target distributions that we have in our set of possible things that we can identify, then we say it's transportable. And so rolling out a policy from one location to another, we might know things about, if the policy was tried out in Maryland, we want to see how it will go in Pennsylvania. We know a bunch of facts about the relative populations of Maryland and Pennsylvania that may or may not be relevant. So incomes, demographics, pool of eligible participants, these kinds of things. We can do some basic calculations and see how the two states differ. We're running a recommender system on our website. We have data from this weekend. What movies did people watch? We want to make recommendations for later in the week. It's not technically the same population. Maybe things will change. But maybe we know something about Mondays. We'll watch different TV shows on Mondays and Sundays. So when can we measure when an effect is transportable? If we had a single population, we talked about in terms of a structural causal model, we could use graphical criteria. Things like the do calculus. We draw the DAG, we kind of figure out which arrows are connected, and we measure the effect. For multiple populations, there's an equivalent, or not equivalent, there's a similar sort of representation in terms of a diagram representing the effects. That's called a selection diagram. And so what makes the source population useful in these problems is that, so if the F's were completely different, Fj were different from F star j for every j, then it would be as if the source population were telling us nothing, and really we just had the identification problem in the new model M star. And so that's fine. We at least can measure that. You can use the standard procedures for that. It's a single model, it's a single population. If the structure is exactly the same, then all we have to do is establish identifiability in M, and then use our identified estimates there, and just apply them again. The non-trivial case is when some components are the same and some components are different. And so this might be, for example, so maybe the response to a policy is the same conditional on household balance sheet or whatever, but the balance sheets of populations in the two states are different. And so we mark the components that are different by adding a node that we call a selection node, Sj, pointing at each variable that differs either in a structural function or the distribution of its errors. They draw these with a square rather than a circle. And so we draw a single graph. We take the one representing the source population and we mark the changes. And so this graph containing these extra nodes is called a selection diagram D, and it contains all the non-parametric structural information about these. So we're not containing the functional forms, but we know which variables are related and which ones have differences. So its use comes from the following theorem, approximate theorem. You can read the paper for the exact statement. The distribution of y given do x can be identified based on the selection diagram if you can reduce y given do x and the selection nodes using the do calculus, which is how we identified causal effects in a single directed acyclic graph, to an expression in which, so any subsets of K have no S variables. So this is saying for K is the set of experiments that we can run. Subsets includes the empty subsets. So in particular, that means that what we want to do is we remove the selection nodes by, for example, noting that they're deseparated given our conditioning, and then we can remove them from conditioning or apply the other rules of do calculus that can potentially express these things in terms of expressions that don't have S, or the other components maybe if it's observable in M star. Then those are the two cases. And so what this means is that we can basically reduce the problem to the do calculus, and I don't like working with that, but my computer is totally fine with it. And so you can just load the causal effect R library, set up the diagram, and it'll give you the identification formula. Go to the Causal Fusion website. So what does this look like? Examples of this. Covariate shift. So here's a selection diagram. The square node says that this variable z is selected. It differs between the populations, and this is just the usual confounding graph where, so controlling for z would allow us to measure the effect of x on y. And so we say that z is S admissible, so selection diagram admissible, if y is deseparated from S given z in the graph where we remove x, where we remove the arrows going into x. What is that about? So basically that's saying if we want to measure the effect of x, then that's doing x removes the arrows. And if doing x, removing the arrows, means that y, and we condition on a bunch of things, and those things deseparate the selection node, then under deseparation, the selection node can be dropped, and it's as if we're working in the new population. So that's a setting. And here, this is a setting which satisfies this. And then the next setting, so that tells us that we can remove in the conditional distribution this. And then the next is, so if z satisfies the backdoor criterion for the effect of x on y, then we have a way of estimating the effect in the original graph. So if we can estimate the effect in the original graph, and we can eliminate the selection node, so that the distribution doesn't matter, the change in distribution doesn't matter, then we can estimate the effect in the target graph. And the formula for that is quite simple. It's so conditioning on y given x and z, averaged over the distribution of z, except the distribution of z in the new environment. And so the proof of this, in the new environment, the conditional distribution of y given z when we do x is the same as, so adding the selection node, that's what it means to add a selection node. But then by deseparation of y and s given z in this graph where we do x, then we can remove the selection node. And so now we're back to something in the original graph. And then do x given z, how do we deal with that? Well, the backdoor criterion holds. So controlling for z is enough to make this a causal pair. And then that gives us the conditional distribution. To get the unconditional distribution, we marginalize over the distribution of z, in this case the distribution of z given do x, so we just average. But by the backdoor criterion, the distribution of z given do x is just the distribution of z because z is upstream, not downstream. So this is basically, if people talk about transportation of causal effects from one population to another, there's a whole mechanism that I just talked about of like various types of models. 90% of the time it's just this formula here. You measure the causal effect in population 1, you average over the distribution of covariates in population 2. It's used so often that people just say that, oh, this is the formula for generalizing causal effects from population 1 to population 2. That's true under structural assumptions. So that's true under these structural assumptions. In these models, it might not be true in other models. And so that's I think why the diagrams are useful, just like, you know, the backdoor criterion is not useful because we didn't know to control for things in a regression. It's useful because it allows us to say precisely when we should control for things. And so this tells us precisely when we should average over covariates. Generalizations of this. So suppose the backdoor criterion can't identify the effect of x on y because it's confounded. I've added a latent confounding to the x to y effect. So that argument I just gave, you can replace the effect of x to y estimate with any other valid estimate of the effect of x to y given z. You still have the S admissibility, meaning, so the selection node that goes into z, once we condition on z, it's separated out from these other things, and so it can ignore it. And then just any estimate of the causal effect. And so if we have, for example, an experiment, and so this might be a reason why we want to do transportation, because in population 1 we have an experiment, in population 2 we have confounding, but we know that the causal effects are the same and we can still rely on them. Note though that what we're assuming here, it's a little bit tricky. We're saying that the only thing that differs, so the only selection node is with the observables. If there were a selection node on the unobservables, we wouldn't be able to weight over it. So it has to be that sort of the observed confounders are enough. But this is useful. It tells you that we can mix experiments and observational studies and identify new things. You could also combine more than 2 populations. So you just create multiple selection diagrams for each source population relative to your one target population. And then you basically, you mix and match. And there are various algorithms for that. They're nasty, but the computer does it, not you. So each part may contribute some component of the identification formula. Okay, here's the thing that you can't deal with. Call this label shift. The selection node now is not on X, it's on Y. And we're still interested in the effect of X on Y. And so here there is no set T such that Y is d-separated from S given T, meaning that we can't use conditioning on something to ignore the selection node. Checked, I ran causal fusion on this graph where I got the pictures from, and it said, no, this is not identified. So here, what's going on, the causal effect is totally different in the targeted source populations. So this, what that node says verbally is, fine, you ran an experiment in city 1, but if you ran the same experiment in city 2, the effect would be completely different. You know, even if it were a perfect experiment. Conditioning isn't going to help that. And so this is a setting where, you know, the diagram doesn't get you out of this problem. It tells you you have the problem. You need additional information if you're going to estimate effects in this setting. What can you do? Well, maybe you can give up on the idea of working with distributions at all. We can think about the realized regret framework rather than the risk framework, and run these various algorithms that don't require any information about the distribution at all, or for there to exist a distribution. So everybody should learn about the hedge algorithm. And then potentially you can realize low regret against an arbitrary sequence against these cases where basically it's saying that the effects are, you know, going to change from one setting to another. You're discarding any information about distributions. You're discarding even the information that there is a distribution, if you have such information. And the cost is that, so this does well relative to a class of policies, not necessarily well, absolutely. That said, if you're in a situation where basically there's no causal effects that have any meaning from situation 1 to situation 2, where there's no point in doing science and learning about the world because the world is just going to be completely changed from one moment to the next. So in other words, if you're a macroeconomist, then maybe this is something worth doing. Performance results for this in macroeconomics are actually comparable to a lot of models that macroeconomists use, which is mostly not a good statement about the hedge algorithm. It's mostly a negative statement about macroeconomists. But anyway, should leave that door open in some cases. But in general, what people do is they add assumptions. So talk about a few of the assumptions that people use to deal with this, this label shift problem where the distribution of Y is changing. So one thing that you will sometimes see them do is say, well, maybe that's not the model. Maybe it's true that Y is the selected variable and not X. But maybe we're in a situation where we just made a mistake and we gave the name Y to the cause and X to the effect. So this is sometimes called the anti-causal setting. And the idea behind it is that sometimes we estimate a predictor or regressor Y given X, even though that's not the direction of the causal effect. And so the fact that the conditional distribution of Y given X will indeed vary when you have a selection node here. You run the regression one, you run the regression in another, and you're not going to get the same settings. But if this causal effect goes the other way, then potentially So this is really actually just a covariate shift problem. We've called the covariates y. And that's tractable. We can deal with that through reweighting. So why does this sometimes happen? Well, sometimes we care about measuring causes from effects rather than effects from causes. Classic example is diagnosis. A doctor wants to predict which disease a patient has. Diseases cause symptoms. And it may be the case that over time, so there's some biological process by which a disease leads to a symptom. There's also some epidemiological process by which the distribution of diseases in a population changes. And there's, say, new evolving variants that show up in your patient population. And so the probability of any particular disease is going to differ. So you're still interested in measuring y given x, or p star y given x. And you might have, so the distribution of x is the symptoms that your patient will report to you, and your biological knowledge, and you might want to use that to learn this. And there are ways of doing this. Note that this is slightly different from the covariate shift because you have the distribution of the outcome, not the distribution of the treatment, but there's this little thing called Bayes' rule that allows you to reverse the order of conditioning. So that's really the sort of practical difference here. The other nice thing about this is often y is low dimensional and x is high dimensional. And this allows you to run like a non-parametric regression with machine learning regression for y given x. But this is basically just saying, suppose you're in the easy setting, even though it looked like you were in the hard setting. So it's not really a solution to the problem. It's just saying, think hard about whether you actually are in the hard setting, because if you're not, your life is a lot easier. Application. So what do people do with this external validity? One thing that they do is what's known as meta-analysis. So you care about a policy. Economists run studies on the policy. They say, is that a good policy? Let's try it. Let's, figure it out. Maybe they run a bunch of RCTs. And so microcredit, Muhammad Yunus won a Nobel Peace Prize for promoting this. And then people had to go and be like, does it actually work to take people out of poverty? And they ran experiments in at least 7 different countries. And measured whether it did indeed reduce poverty and have various effects on the outcomes for these individuals. So we want to know, does this work? And we have 7 different populations. We want to know, we open a microcredit institution in a new country. Do we think that's going to work? If all the studies are externally valid, we can just average all of those effects and get a more precise estimate. If they're transportable, for example, because the differences are only in the predictors, so various covariates that are involved, then we can estimate conditional outcomes and then pool them with weighting and get, again, a more precise estimate, accounting for the fact that the income of households in Morocco and Kenya is somewhat different, and maybe that is the main difference. A more agnostic perspective might suggest that these studies differ not just in their covariate Z, selection node going to Z, but also in their outcome nodes Y. So it may be the case that it really is the case that this treatment just does something different in Morocco and Bosnia. X has nothing going into it because it's an RCT. So we can check, is this non-parametrically identifiable? nope, we can't deseparate this node going into Y. This is a case of it. So we have the covariate shift here. We also have the outcome shift. So what do we do? Well, a Bayesian perspective is another decision theoretic perspective, is that we can think about the effect across all populations as a draw from a distribution. Any parameter you can treat as a draw from a distribution. You know, there's a causal effect in Bosnia, there's a causal effect in Morocco, there's a causal effect in Kenya, there's a causal effect in Bangladesh. I think one of these studies, I don't remember exactly all the countries. Even in the absence of identification, the Bayesian perspective will get you a posterior distribution over this distribution of effects across countries. And so one thing that we might add, this latent effect heterogeneity distribution that's inducing these changes with respect to the target is exchangeable. The joint distribution of structural functions across all studies is invariant of permutation. So maybe not necessarily IID, but the fact, you know, the naming doesn't necessarily matter. What this will allow us to do is say that one more country, we can treat this as a new sample from this set of draws. So if more and more studies were added, we get more and more samples, we learn the distribution, joint distribution, and we can measure the degree of selection. And so you might, so in this particular study, they use a normal distribution conditional on covariates, so just binary access to microcredit indicator with some variance, and then a normal prior across studies. So this normal meta-analysis model is fairly commonly used. So if the variance across studies is 0, we estimate that. The conditional effects doesn't vary across studies. We have learned that this node is inoperative, and we can just exactly pull all the studies and average. More generally, we get a posterior distribution, which probably won't have this v at exactly 0, and we get we can get a posterior predictive distribution, which will tell us at least what the distribution of differences across studies is going to be if we send this to a new country. So in practice, this normal prior will just turn our results into some weighted average across the studies with a weighting that depends on the relative variance. And the thing about studying this with respect to a selection diagram is it tells you exactly when that's reasonable. So it tells you that the weighting component of it with respect to, so using a regression with respect to covariates, that's justifiable under selection node on Z. The heterogeneity induces a selection node on Y. If you don't think that this is your model, then maybe you want to use a different meta-analysis model. So in particular, if you're not just using RCTs, weighted averages might not be what you want to rely on. Okay, so that's external validity. Basically said, if it's in the covariates, you're good. If it's in the outcomes, you're bad. And so, you know, be Bayesian and have a posterior that doesn't contract, or be, you know, an online learningist and use a low regret procedure. Next issue, sample selection. So data on some units or variables may just be missing. And the observations that make it into a sample may not be representative of the population. Even if the setting is unchanged, just because you didn't get observations that look like the full population, you got observations that look like some selected subset of it. So this is called the sample selection problem. Note that this is not the same as selection to treatment. We talked about selection bias there, the different selection. It's also not the same thing as what's described by selection nodes. Just people use the word selection to mean that anything is related to anything else. And so if somebody says that you have a selection bias problem, just please ask them to write down an equation, because there is no way of just, if somebody says selection, of telling what in the world they mean. Presumably we should have come up with other words for this, but we didn't. So, okay, so we're in the sample selection problem now. I'll try and say sample selection, but I might just say selection sometimes in heavier turbine context. Some variables in a system determine the chance that we observe a particular unit or a particular set of attributes. This can happen due to survey design. You might deliberately be sampling more units in some locations or groups or attribute classes in order to improve the precision of your estimates. That's a common thing that's done. So, you know, if you care about certain rare groups, maybe care about health status and there's some disease that most people don't have, you might want to oversample people with that disease. You may have non-response because only certain groups are likely to respond to whatever survey method it is, basically any survey method. Some people just won't pay attention to you if you call them on the phone or email them or knock on their door. And the extent to which this matters will depend on some sort of model. So we always have a sample selection in the sense that you know, we don't have the full population in our samples, and so, you know, something is deciding who those people are, or which units those are. But if we have random sampling, what that means is it's unrelated to variables in the system, and it's so no different from, in terms of the analysis, from having a smaller sample size, which, you know, is not great because of these generalization issues, but not terrible if our sample size is large enough. In other cases, the sample selection, because it depends so intimately on the actual variables, results may not even be definable in terms of population. So it may be based on the structure of the relationships. So you might not observe the wage for some people because they're not employed. And so the fact that the wage column is empty for some people is not just a coincidence. And it's not that there's some, you know, what their wage would have been out there. Or maybe there is, but you need to define that counterfactual very precisely. Health outcomes. So if you give a pill to some patients and half the patients who get that pill die, and then you try and measure the blood pressure of patients in response to your pill, you can't measure the blood, well, I guess maybe you can measure the blood pressure of people who are dead, but in general, most of these health outcomes simply are not defined in this sort of setting. And that's very relevant to the performance of the drug. So how do we model this? So we treat selection into a sample as a variable along with all the other variables in the system. We denote it by a sample selection indicator, which is also going to be called S. And it equals 1 if the observation is included and 0 otherwise. And so the unique feature of a selection indicator is that because you only see the sample if S equals 1, the observed distribution is always a conditional distribution, not an unconditional distribution. And so if this applies only to variables some variables yj, we get the conditional distribution of these variables, at least, but makes the others unconditional. And so in a structural causal model framework, we represent it by adding a node, S, that may depend on other variables, In some of these papers in the causal fusion software, in a lot of these papers, you'll see it as a node with two circles around it to indicate it's a selection node. And it has arrows going in defining the determinants of sample selection. But in general, it doesn't have arrows going out because it's not something that's defining effects in the system. It's just defining whether you, the observer, get to see components of the system, which usually doesn't itself determine things, though, of course. May indirectly determine things through your study. Note the contrast with transportability analysis, where we also called things that are very different selection nodes. Those nodes have arrows going out of them, but not into them. They reflect differences across populations. Here, these sample selection nodes have arrows going in, but generally not out. Once we treat these as nodes, non-parametric identification follows from the usual analysis for structural causal models, with the restriction that the observed data is always conditioned on S equals 1. And so if we want to identify a causal parameter in the population, given selection, it needs to be the case that its distribution can be identified in terms of observables conditional on S equals 1. So generally speaking, what that means is that we're going to need to be able to remove this S equals 1 from our expression in order to estimate a causal effect. So simplest case, just to show you what this looks like, S is not linked to anything. Here's our selection node, maybe X causes Y, and then selection is just independent. If that's the case, conditional and unconditional distributions are identical. You can drop any variables with, you may have missing values for a bunch of variables, but it's totally fine because the variables that have missing values are not determined by anything at all. And so it's okay to drop something with missing variables. This is a default behavior in a lot of software. I think it's, so is this a good model for your outcomes? I don't know. Is this the model that when you run a linear regression and you have missing data in some of your rows and columns that it will run? Yes, a lot of the time it is. So, you know, the importance of this model is that it's what's being assumed by default when you run software a lot of the time, or at least something very much like it is being assumed. It is sufficient to justify the behavior of the default behavior of a lot of software. Not all software has this default. Some software will loudly yell at you and give you an error message, and that's annoying, but also potentially desirable because it will make you actually think about whether that model is reasonable. Other examples, so y given x and s equals 1 is equal to a distribution of y given x if and only if y is d-separated from s by x. So the if follows directly from the definition of d-separation. The only if is a theorem. And so basically what that says is that you can ignore selection if the outcome is conditionally unrelated. So if selection depends on the treatment, there's a map from x to s, you're good, you can ignore it. It's equivalent to just having a different portion treated in the experiment, and that may affect the relative sample sizes, but it doesn't affect your estimates of the causal effect. Suppose instead, there's an arrow from y to s, or an unobserved relationship between y and s, so a common cause between selection and the outcome, then this is as if the outcome distribution has changed. So, you know, you've dropped all the large outcomes or all the small outcomes or the outcomes with some particular set of features that is going to change your estimates of the effect. And here, because it's directly related, there's nothing you can condition on to separate this out. So selection based on X, fine. Selection based on Y, big problem. You should especially be worried if this is coming from, so if your non-response to your outcome survey is coming from difference in outcomes or variables that affect them. So the people who benefit from the program might be deciding based on their new resources to go and leave the country, and so your program will look bad. So various studies of, you give people money and the first thing they do is they were living somewhere that they didn't want to live because they were poor, and then they leave and you'll never find them again. That, underestimates your effects, or it could be that whatever program you're doing is so terrible that people decide not to come back and they never want to talk to you, and then, you overestimate your effects. What if it's based on covariates? So if S is linked to Z and maybe X. So this is something where it's a little bit difficult. So it depends on which variables are not observed if you have selection based on covariates. So this can be done in the case where we can combine multiple data sources, some of which are subject to sample selection and some of which are not. And so very often we have unselected measures of covariates, so unconditional measures of covariates, and we just have selection for the outcome variable. So this is because we observed the covariates in a baseline survey, then we ran the experiment, and then we had a follow-up survey to measure the outcomes, but in between those two time periods, somebody disappeared. And so we have the unconditional distribution of the covariates, but not the distribution of Z. Another reason might be that we know the population distribution of the covariates because it comes from some sort of census or administrative data set. If we're in this situation, which is pretty common, then there's a version of the backdoor criterion that works. Notice that I've drawn this graph where if there weren't a selection node, this would be just the standard confounding graph where we could estimate with backdoor. So if we know the distribution of Z's, and Z satisfies backdoor, so this paper has a generalized backdoor, not important, and then why is D separated from S given X and Z? What is that? Well, okay, if we're conditioning on X and Z, which is what we wanted to do for the backdoor, then we can ignore S. So that's great. We can run the backdoor and we can ignore S. Then what is the effect that we get? Well, we estimate, again, the conditional average by the backdoor in the selected population, conditioning on X and Z, and then we average over the unconditional distribution of Z, which we get from the baseline survey or the census or whatever it is. So again, just like in all the other previous cases of so external validity, transportation, there's some version of, there's a backdoor criterion, the conditional estimates given covariates, and then you weight it with respect to the covariates. And so you can see why I had same lecture on these multiple different components, because the estimates are essentially the same, except here we're conditioning on selection nodes. In other cases, we might be conditioning on population differences, so on. How do we do estimation in this case? So it's like the adjustment formula. You take a regression and average, except now we're averaging over something different. To get this. So I didn't mention it, but we need an overlap condition for the distribution of X for this distribution that we're averaging over to have a support that we can measure. So the distribution of S equals 1 and X equals X given Z should be, the probability of that happening should be non-zero. And then one thing we can do is we can estimate the conditional mean this thing in the center of the average, y given x, z, and s, where s is we've conditioned on it already because it's in our sample, and then get an estimate of pz and average over that. So if we have a bunch of samples, we can use the empirical distribution. If we have a census, we can use the census distribution. If you're using Bayesian regularized regression for these mean estimates, this procedure is called multi-level regression and post-stratification. And so if you listen to some of the Bayesians who advocate this, this is the solution to sample selection, which is fine if your sample selection problem is one of the ones where the selection backdoor criterion applies. Is when you would want to do that. Otherwise, it's not the right identification formula. But this is sort of the causal justification for that practice. To have a regression-based estimate, we should have an inverse propensity estimate. You estimate here, now there's two propensity scores here. There's the propensity to be treated and the propensity given z, and then the propensity to be selected. So you take the inverse propensity weighting formula, and this average is conditional to the expectation of the indicator of x equals x and s equals 1 divided by the conditional probability of those. But that conditional probability can be expressed as the product of these two treatment propensity score and selection propensity score. So you just divide by those propensity scores, the average, you average here over the z distribution, the empirical distribution of outcomes. Regression, inverse propensity, augmented inverse propensity. Same AIPW formula. So you take the product of the indicators of the treatment and selection, you subtract the mean, you divide by the product of propensity scores, you add back the mean, you take the average of that. It's doubly robust, you can sample split, use machine learning, blah, blah, blah. There's an R library for that. It's nice. It's basically the same as the usual AIPW estimators, except you just have two different propensity scores. So outcome-dependent sampling. So this was the case that we talked about. So there's your selection node is associated through latence with y. Y is associated with S. So here, this is not non-parametrically identifiable. So classic example, your labor market program impacts wages, but the workers who have bad job prospects may decide not to enter the labor force to begin with, and so their wages are not observed. And so it's precisely because these job prospects are a latent variable that determines both wages and employment. So we have this outcome-dependent sampling. So what do we do? Well, in practice, people for decades have been applying much stronger assumptions than just which variables are related to which ones. Jim Heckman came up with a parametric model of this. Suppose X is always observed, Y is sometimes observed. Assume everything is linear, Gaussian, homogeneous. Selection is driven by a latent variable that's driven by a probit model. With all of these, you obtain identification, basically due to the nonlinear form of the selection equation, which is an indicator of the linear effect of treatment. So how credible should you think of these functional forms? Well, it turns out that under very similar assumptions, Heckman showed that the distribution of y given x is identifiable with zero information on y at all from anyone. He used this to write a paper entitled The Effect of Prayer on God's Attitude Towards Mankind. So prayer, found a data set for that. The y variable in this, he didn't have data, but you can make some functional form assumptions. And so this paper was either a major advance in quantitative theology, or possibly a warning that these functional form assumptions are extremely, extremely strong, and maybe you should think very hard before using them. One of those two things. So what else can you do? I'll just go through this briefly. You can add additional assumptions and also restrict the observations for which you can measure a causal effect. So not for the full population, but for a subpopulation. And so here assume a binary x. So same causal graph as before, this causal graph x causes y, x maybe is causes s, and s is associated with y. And so we get potential outcomes y1, y0, and potential selection s1, s0, given treatment. Causal consistency for these will follow from the graph. And assume that we see x always, and selection always, but we don't always see y. We see s times y. We see y if we're in the selected setting. If x is an experiment, we can assume it's independent of the potential outcomes for y and s. And then the thing that we can add to get some traction here, which you have to justify in your particular setting, is monotonicity of the selection equation. So given treatment, you are always as or more likely to be selected. So you may not be selected either time, you may be selected both times, you may be more likely to be selected, but you are not less likely to be selected. You could also flip the sign and be monotone in the other way, and then you reverse the sign of all these arguments. If this is the case, you can learn a local treatment effect for the always takers. So those who would be in the sample regardless of treatment. And so the idea behind this is that the counterfactual y0 for the always takers is point identified, because for the selected ones who did not get the treatment, then you know that these people must have been always takers. So because you know that their S0 equals 1, they got selected even under D equals 0, but by independence, that doesn't, the D equals 0 doesn't matter, so this is among the S0 equals 1 crowd, but if S0 equals 1, S1 must also equal 1. So if they're selected, even without treatment, they must have been selected no matter what. And so we can get y0 among the always takers. For y1, it's either always takers or compliers. And we don't know who's which, but what we can do is we can say that, well, the maximum y1 is the case where the largest values, the largest quantiles of y, the largest y1 for always takers is the one where the always takers are the ones who have the largest values of y. And the smallest value of y1 should be the ones where the always takers have the smallest quantiles of y among the proportion of always takers, which is identified by an argument that I'm not going to go through because I'm over time, but you can see either the original Lee paper or this nice paper by Semenova which does so this is the unconditional argument. If you have all of this holding conditional on covariates, then you can do these estimates conditionally. If you have conditional monotonicity, and then some averaging will get you tighter bounds. So that, the Lee bounds, there's software for these, the original Lee bounds. I think Simonova might have software for her new stuff, but I couldn't find it. This data command, even for this. So this is like, you add monotonicity, and that's not a terribly strong assumption in some cases. At least you can imagine it happens. It's probably better than linearity, homogeneity, Gaussianity. The other thing that you can do is that there are versions that use an instrument for selection. So something that affects S but isn't associated with or directly causing Y. So that approach was actually introduced in the original Heckman paper. And if you have an instrument, you're not relying just on those linear functional forms, though you are relying on monotonicity, homogeneity through a probit index and sort of the Gaussianity there. It's sort of a slightly weaker assumption if you have a valid instrument. It turns out that there are approaches there that don't rely on Gaussianity, so long as you still have homogeneity of effects. So you have a single in monotonicity, you have a single index describing them. And then if you get rid of homogeneity, you still need this sort of monotonicity form. But if you have a valid instrument, you can get a conditional effect among the subpopulation with S equals 1. And the causal weight R library that has these non-parametric double machine learning selection corrections for selection based on covariates also has this IB version. So you can try that too. And so you can use this. So meta-analysis, the meta-analysis I described, there's only the external validity problem. But arguably, the process of how studies get chosen is also a thing that potentially can bias the distribution, the meta-analysis, from the distribution in the population or target of interest. So you can have what's known as site selection bias, which is just sample selection bias into the sample based on attributes, because people run experiments in places where it's convenient, not necessarily in places that have representative or transportable effects. So there's a lot of studies in the US, certain cities in the developing world have good experimental infrastructure, most of them don't. You're not going to get a lot of studies in those places. You may also have selection based on the outcome if the editors are selecting on large, surprising, or otherwise interesting outcomes. This is what's known as publication bias. So editors or researchers who anticipate the behavior of editors. So this is outcome-based selection, so it's not non-parametrically identifiable, but fortunately we know a lot about its structure. We may have non-selected replication studies that can allow us to estimate this. We may also know some things about the functional form. For example, that there may be a discontinuity at p equals 0.05 in selection effects. And so both of these can potentially be used to estimate and identify a corrected distribution. So these are the kinds of things where you want to go from estimates to outcomes in a population. So sampling variation, fitting process will induce generalization error between our estimates, which we can measure with generalization bounds and reduce by regularization and use of holdouts. Population distribution in which we do the estimation may differ from the population distribution in which we want to run the policy. That is describable as a lack of external validity. And using selection diagrams, we can characterize when effects can be estimated and identify transportation formulas that allow us to identify and estimate based on the combination of data. And then our sampling processes may systematically be failing to observe certain units, causing sample selection bias, which using sample selection nodes, we can describe when those effects are identified, or potentially making additional functional form assumptions. And so together, taking into account all of these ways can allow us to have potentially more robust estimates of causal effects. It's the kind of thing that often an individual study, unless there's clear sort of sample selection bias in that individual study, you often are not taking into account. But if you're going to actually apply these studies or use multiple studies, this is an important component. So that's it for today. That was the last sort of topic lecture for the class. Next class, we'll have a discussion of what your research is. This can, be open-ended, and I'll try and, provide you some feedback so that you can proceed with that.